In this video we're going to be discussing Linux file permissions. So permissions basically allow certain entities access to a particular file or directory. Okay, there are three entities. There are the user entity, and that is the owner of the file. There's the group entity, and the group is a Linux concept. It is part of the operating system, so every user has a group that they are a member of, and any other members of that group, they have particular access. And then others is everyone else. So the three entities: user, group, and others. And for each entity there are access modes, three different access modes. You can read the file, you can write to the file, or you can execute the file as if it were a command. Okay, and we're going to talk about these three things. So the first thing we want to look into is the ls command. Okay, so if we type ls, and I'm on my desktop here, ls-l, -l lists out every item, one per line, and we see we have a few things on my desktop here. The shell has highlighted this item in blue, and what we're going to be focused on here is the permissions on the left. Now this item in blue is actually a directory, and we see a D right there. Okay, so these are the permissions. That first bit indicates whether the file or the entity, the inode is a directory or a file. These 9 bits here represent the user, so the first 3 are the user permissions, that's read, write, and execute. The next 3 are the group permissions, so the group has read and execute permissions, and then the next 3 is everyone else on the system. So everyone else can read this and execute it. So with directories, you do need to be able to execute them to enter into the directory. Okay, it's not enough just to be able to read it. To read it, you can read the name of the directory, but to execute and look inside of it, directories, you must have the executable bit. Okay, when I say bits, this entire grouping of permissions here, these are actually stored on the system as bits, ones and zeros. So if this directory bit is a 0, the ls command displays it as a hyphen, right? If the read bit here is a 1, right, it shows it as an R, because that's indicative of what that particular permission is supposed to represent. Right. The alternative, if we look over here, in this example, we have a desktop directory and some other files. What's actually stored on the system is a series of ones and zeros, but that's not very easy to read, right? So the system, the ls command, whenever it sees a 1 for that first bit, that's the directory bit, and so it displays a D for us. That helps humans understand, but the way it's actually stored on the system is just ones and zeros. Okay, so the next 3 bits would be 111, right? But if it's a 111, it displays the actual permissions that you have. So it says read, write, and execute. Okay, so the ls command is just making this nicer for human consumption, right? But what's actually being stored for each inode, each directory or file, is a binary string, or a set of binary digits that represent the permissions. Okay. So again, we have 3 entities: the user, the owner of the file, the group that user is in, and then everyone else. And then 3 access modes: we can read, we can write, or we can execute. And to view these permissions, ls-l is going to be our friend here. All right. So one thing we need to look at is the entity octal digit. Okay, so in Octal, it's base 8. So how many different ways can you enumerate 3 digits, 3 binary digits, right? We have 000, 001, 010, all the way down, right? And if we look at this in Octal, which Octal means base 8, so there's only 8 symbols. So 1 through 7 is 7, and then 0 is the 8th symbol. So for 1 digit of Octal, you can represent 3 digits of binary. Okay, and we see that the binary versions of these 3 permissions per entity, right? We have a block of 3 permissions for each entity. So if that binary number is 000, the ls command would format that as hyphen hyphen hyphen, right? All of the access modes are off, right? If there's a 1, it means that access mode is on. So 001, this would be how ls prints that out. It means you would have the executable bit set. If you have 010, that would mean you have the writable bit set and nothing else. 011 means you have, that should actually be the executable bit. So read comes first, right? So if you have 011, the read bit would be a 0, and then the write and executable bit would be set to 1. Here we have 100, the read bit is set, and the others are set to 0. Then we have 101, read is set, write is 0, and executable is set. And then 110, read, write, and then executable is not set. And then 111 is all the permissions set. Okay, so that's a nice little chart. But the interesting takeaway is that all 8 of these possibilities, this is every possibility, every combination of these 3 access modes, every combination can be represented by an octal digit. Okay, so the most common ones you're going to run into is 7, which means all permissions. So when I'm changing permissions, when I reference the entity octal digit 7, that's the same as saying 111, which is the same as saying all permissions. Okay, 6 is saying everything but executable. 5 is saying everything but you can't write. And then 4 is saying read only. Okay, so these are the most common. These top ones are the most common you'll see, and you'll also see 0, because that will shut a particular entity down from access, right? So here we could shut down others from having access if we made this all 0s. Okay, so this entity octal digit, this is kind of a shortcut for the permissions, and you can memorize what these numbers mean, but these are the ones you're going to see the most. Okay, so now how do we modify the permissions of a file or directory? Okay, so we can use the chmod command. It stands for change mode. The ch in change and then mode. It changes the access mode of the file for a given entity. All right, so the most common way we're going to be able to change the mode of a program, at least in computer science, is we're going to be modifying a file so that it's executable, so we can run it like a program. All right, so here we have a few different versions of a simple hello world program that takes in arguments and then prints them out. So we have it in 3 different versions, hello world, and this is a C program. And notice none of these are executable. None of these have the executable bit set. The user is read, write, and no executable, which is 6 on our chart. Read, write, no executable bit. And then the group and the user is read only, which is 4. Okay, so this is a common setting. The octal version of this is 644. Okay, so you might see change mode to 644 a lot. That means it's not executable, the user can write, and no one else can write. All right, so in computer science, like I said, we might want to execute a program as if it were a binary file, right? So the system can actually run it. So in C, this is what a simple hello world program looks like that prints out arguments. And so if we compile this, notice this is just a text file. I'm opening this up in a text editor, and all of these programs are just simple text file. This is the same program in JavaScript. It says hello world and then prints out the arguments. This is the same program in Python, hello world, and then prints out the arguments. And then this is the same program as a bash script or a shell script. Right, it says hello world and prints out the arguments. Now for each one of these, with the exception of C, we won't talk about C quite yet, but for each one of these I can run an interpreter. So bash is a program, and I can pass in a script file. So hello world.sh. And what's going to happen, this bash program is going to read in this file text and execute each line one at a time as if the commands were part of the shell. Alright, so if I execute this, I can pass in arguments as well. I can say red apple and yellow banana. Okay, so in quotation marks, I've red apple. The quotes mean that space is part of my argument, or I can use a backslash to indicate that this space is part of the greater argument, because arguments are separated by spaces. So if I press enter, we see that this file is now executed as bash commands. Right? It says hello world arguments. We have red apple as one argument and yellow banana. We can do the same thing for Python 3, but we have to use the Python 3 interpreter. So Python 3 hello world.py, and we'll do the same thing. Red apple, yellow banana. All right, basically the same program, right? Python includes the name of the file as part of the argument, and then after that, any arguments that are provided to it. Right? But notice again, we had to provide the interpreter. What program are we trying to run this text file with? Okay, in Bash, we had to provide the bash command and then provide the path to the file. Python 3 is the Python 3 interpreter, and then we provide a file name and then any arguments. Same with JavaScript. We have node hello world.js, red apple, yellow banana. All right. Now in node, it includes the path to the node binary as the first argument, the path to the file as the second argument, and then the additional arguments. Okay, so every kind of programming languages may do this slightly different. All right, so these three files are just text, and we can run them even though if we type ls-l, there is no executable bit. But the only way we can run them is by using the actual program as the command and then specifying the path to the file as an argument. Okay, so these commands are actually executable. Our file is not executable. Okay, now it's a little different when I try to run the C program. So with C is a compiled language, so we have to use the C compiler, which is GCC, and what do we want to compile? Hello world.c, and we want to create an output file and then hello world, and I'm just going to not give it an extension. Okay, kind of like all these commands, these are just binary files, but they don't have an extension, so I'm going to leave the extension off because this is going to be executable. Alright, so now when I type ls-l, it has created this additional file, and we see the permissions. It set the permissions. The executable bit is set for each entity. Okay, so now I can execute this. Look in this folder /hello world, and I can execute it just like a program, like the ls command or GCC or node. I can execute it just like a program. We'll do A, B. Okay, so the other option here is I could move this file into a folder that's included in my path. Okay, so my path is a series of directories, right, separated by colons, and if I place any programs in here, anything that's executable, then at the command line, when I type in that thing, the shell is going to look in each one of these directories to see if there's a program that matches the command that I typed. And if there is, it's going to run it, and it's going to look in this order. So here, one of my directories in my path that I've configured is in my bin directory, in my home directory. Right? Bin stands for binary. That's commonly when you see bin, that means there's executables in that directory. So I'm going to move this hello world program that I compiled from C. I'm going to move that into my home directory /bin. Right? I type ls-l, we see that's gone. But since that's in my path, I can now just use hello world like a command. Okay, so that command, that I just created that, and I put it in a directory that's in my path, and so now I've essentially just created a command that I can use in any directory. I can use this if I'm in the root directory. I can still call hello world and it runs just fine. I can run it wherever I am. Okay, so that's kind of the power of the path, right? But in order to run these programs, they have to be executable. So what about our Python and our Node and Bash, right? What if we want to run those as executables? Well, there's a trick. You can do it. All right. So what you have to do is you have to set the executable bit. All right. And then also at the beginning you have to set what's called a hash bang or a shebang. Okay. The hash bang, since these are just text files, the hash bang tells the shell what program you want to run this text file with. Okay, so it's called hash bang because that's the hash character, and then the exclamation point is commonly referred to in the shell as bang. So hash bang, and then this is the path to the env command, and then what interpreter do I want to use? So this is a bash shell script, so I'm going to say bash here. Now you could also do something like /bin/bash. Okay, and this is basically the path to the interpreter you want to use. Okay, but on different Linux systems, sometimes it's not located in that same spot, which is why commonly you say user/bin/env and then specify the interpreter. Okay, so this is a bash script now, and I can change the mode to make this executable. So here, I have no executable bits on my user, my group, or anyone else. To change that, this is probably the most common way you're going to use chmod. I can add the executable bit, and if I just say +x, that adds it to all the entities, and say hello world.sh. Now if I type ls-l, we see it's been colorized green, but the reason it's colorized green is because the X bit, the executable bit for each entity, has been added. Okay, so now I can run this like a program. And even though it's just a text file, since I have the hash bang, this tells the shell what interpreter you want to use to interpret everything in this file. So because I have specified bash here, when I run this file, just like I ran the C program, /this, the dot means I look in this directory and run the program hello world.sh. Okay, so now I can run this just like it's a program, and I could rename that and get rid of the .sh and put it in my bin folder just like I did with the C program, and we'd have hello world accessible as a shell script, but it would be accessible as a command. We can do the same thing for all of these. Okay, so the Python, if we look in Python, we would have to add the hash bang user/bin/env, and then what's the interpreter we want to use? Basically, what command we want to use to run this text, right? We want to use the Python 3 interpreter, and so we go back here, chmod +x, hello world, and this is .py. ls-l, it's now executable, user, group, and others. And now I could say hello world.py. Right, and that's the Python version running. And then the last one would be Node, so the JavaScript. So Node is the JavaScript interpreter, so we can say hash bang /user/bin/env, and then we're going to use Node You want to make sure you have the Node interpreter installed on your system in order for this to work. Same with Python. Bash is usually installed by default. But either way, this is the hash bang for Node, and we want to chmod plus x hello world.js ls-l. It's now executable, and we can run this. Okay, and that we see that's the Node version. All right, and then also this this directory here, right? Because this is the executable bit, we can navigate inside of it, cd into hello, and we have world in here. We can see what's in that file, ls-l. So that's just a text file, and we can cd ... Now, if I change permissions of this directory, so I do not have the executable bit, ls-l, right? So what I want to do is chmod -x to hello. That's the name of my directory. I run that, and I say ls-l. The executable bit is gone on that directory. And now I can no longer change directories into it. Permission denied. Okay? So that executable bit is important for being able to actually access the contents of a directory. So chmod plus x hello. And now I can cd into it. Okay? So that's the basics of the chmod program. We're going to be using it mostly with just plus x and minus x. But going back to the entity octal digit, right? There are many different options you can specify. So if you wanted to lock down your program from anyone else having access, but you wanted full access, read, write, and execute, so you would do chmod 700. Okay, so here's an example. If you have the octal 640, the 6 would be the user permission, right? That would be user read, write. The group should be read. Yeah, there we go. Group equals read permission. So 4 is a 100, right? And then the last octal digit is the others, and it's going to shut that down, and there'll be no digits, right? So 6 gives you read write, 4 gives the group read, and then the 0 at the end gives others no access. Okay, so this is another way you can use chmod instead of the plus x or minus x. You can say chmod and then specify 3 octal character or 3 octal digits. The first octal digit would be for the user, the second for the group, and then the third for others. An alternative way of doing the exact same thing is use this format. So you specify the user entity, you set it equal to the 2 permissions that you want, 2, 3, or 0. Right here we have the other entity, and we set it equal to nothing. So that's going to set everything equal to 0. So this is the other format you can use. Right? So chmod, set your permissions, and there's a variety of ways you can do that. You can do plus x, plus r, minus r, any of that. You can use the octal version, or you can use this expanded version. Okay, there's no spaces between any of this. You separate the entities with commas. Okay, so entity equals permissions, comma, entity equals permission, comma. Right, and so here would be some other examples. Chmod 755 means everybody has read and execute permissions, but only the owner has write permissions. So only the owner has that W. Okay, group has read, execute, other has read, execute. That's Octal 755. Another common one is Octal 644. Nobody has execute permissions, but only the owner has write permissions. So user has read write, group has read, and other has read. Okay, and then if you want to recursively change the permissions in a directory, of a directory and inside of it, You can't use dash lowercase r because that's going to remove the read bit. So to do recursive permission changes, you have to do dash capital R and then specify the permissions. Okay, so that's permissions in a nutshell. You can always look back at this chart. Remember the octal digit. There's one octal digit for every 3 binary digits. So what that allows us to do is for each entity, since there's 3 bits associated with each entity, we can specify one octal to represent all of the permissions for every entity. So again, 755 is common, 640 is read write, and then read, and then everyone else is locked out. You might see 700 a lot. That's the user has all access. Others have nothing. Group has nothing. You might see 600. That's read and write for the user, and then nothing for the group or the user, or others, I mean. Okay, so that is the chmod command. And it should be noted that there are also other permissions, more advanced style of permissions in Linux called access control lists. But this is the basic style of permissions that are used, and it's going to allow you to execute your programs, which is the most important thing, most important takeaway. So make sure you use +X to make your programs executable, and then make sure you add your hashbang, and that will allow whatever programming language you're programming in, you have to specify what interpreter you want to execute this code with. Okay, so that is Linux permissions in a nutshell.